Okay, hello everybody. I'm Ivan Smalyuk. I'm coming from University of Colorado, and today I will be discussing the Hopf and Skirm solitons in liquid crystals and liquid crystal ferromagnets. So the students and postdocs who did the research work I'll present today. Um, Haley Son, former student, Paul Ackerman. Haley is also current PhD student, and Benny Tai, current PhD student. And so the more familiar type of solitons for people working in fluid dynamics are these type of big solitons you can generate in the waves on water. And so this is not what we'll discuss with you today. Those will be the solitons that are micrometer or so in length scale that can behave very much like colloidal particles, and as you can see in this particular movie in here, can self-assemble, also can exhibit very rich types of out of equilibrium behavior in many ways, resembling different types of active matter systems like these herds of animals in here. And so before we, however, proceed with discussing in details the behavior that these solitons exhibit, I would like to remind something you might know from high school, but nonetheless, it's useful to recall the basics of homotopy theory, and in particular, the sphere-sphere maps that are often very helpful in understanding what types of topologically distinct structures can be realized in different systems and different types of fields. And so much more commonly, we study singular defects, especially when it comes to condensed matter systems like liquid crystals. And so in this case, if we have a singularity in a two-dimensional system, for example, in magnetization field, like the ones you can see in here, we can characterize them by mapping from this sample that we have to the ordered parameter space, which in case of the magnetization confined to two-dimensional plane would be simply a circle. And when we do this mapping by surrounding the defect by another circle, right, we will see that depending on the structure we have, those two different topologically distinct structures will have different integers. Right, so in here, it's a map from S1 sphere or circle to another S1 sphere. And in both cases, we get integers, 1 or 2 in the other case, right? So those are the elements of pi1, S1 group, and this is how we typically label them. Now, we can also have point defects in three-dimensional space. Here we would surround them by S2 sphere. For vectors, in such case, the order parameter space would be a unit sphere that describes all possible orientations of a unit vector. And again, we get integers, so we can have different integers describing how many times we will wrap these field configurations when we map from one type of sphere S1 or S2 to the other sphere that corresponds to the order parameter space. And so this is very useful in characterizing the different types of topologically distinct structures that we can have, very much so like, we can distinguish the topologies of spherical surfaces from those of toroid and so on the basis of genus. And here, the topological invariants that we will deal with will be these integers characterizing the field configurations. But we can also have other types of topological and non-trivial field configurations when actually we don't have regions in space where the field is not defined, right? Like in these cases, we have points and those could be also lines and walls, where the order parameter is undefined. We can have perfectly continuous field configurations, yet topologically non-trivial. And so in here is a visualization field is confined to two-dimensional plane, so it can only exhibit different orientations confined to that two-dimensional plane. And so we can see that when we have this type of rotation or magnetization by 2 pi, this field configuration localized within this spatial region in one dimension cannot be removed by wiggling those pins of magnetization. This uniform background can be extended to infinity. However, within the small region in this along the x coordinate, we'll have a one-dimensional topological soliton. Now, you could ask, what does it have to do with the sphere-to-sphere maps that we discussed earlier? Well, you can appreciate that with uniform far-field background, right, we can extend this one-dimensional system to plus and minus infinity, and this becomes then a circle, and we then again would be mapping from an S1 sphere to the order parameter space, which for this system with all possible orientations or magnetizations confined to 2D is also a circle. So it's again pi 1 S1 type of topology that we deal with in here. Now, in a similar way, we can have also two-dimensional topological solitons, and so here we can relate the structures in two-dimensional system or R2 with those on a sphere through a simple stereographic projection. And always when we have uniform far-field background, it is possible to represent such continuous field configurations in two-dimensional system R2, also on the sphere S2, right? And so in here you can see two different types of two-dimensional topological solitons. Also we'll call them baby Skyrmans, and the reason will be clear in a couple of minutes, that can be represented as smooth topological non-trivial field configurations also on the S2 sphere. And so now those can be mapped to the order parameter space, which in the case if we allow to the magnetization of spins to point in any possible orientation, then it's again a unit sphere, right? And so we'll have the pi to S2 topology. So the integers will correspond to the different number of times that we will cover the S2 sphere when we'll map field configurations from two-dimensional plane or S2 sphere to this another S2 sphere, the order parameter space. And so recently the so-called two-dimensional Skyrmans, often also called baby Skyrmans, are very popular in magnetic systems, in particular in the studies of non-centrosymmetric magnets. And one of the motivations there is that such Skyrmans can be used to store information. And in particular, one type of data storage approach that's envisaged is to use them in so-called racetrack memory devices, where such topologically protected and energetically favorable field configurations that behave like particles can be created and then stored somewhere. And then when you need to read and write information, you would run them on such a racetrack and read and write information. So the size of these magnetic Skyrmans can be sub 10 nanometers, and so this would allow to have quite dense data storage, also because with racetrack memories you would not have to be confined to 2 dimensions, but could also go to the third dimension and store them, elsewhere, not necessarily within these racetracks. Comes from a high energy / nuclear physics theorist who was actually working at University of Birmingham during most of his career, also in other places like Los Alamos National Lab and so on. But the types of skyrmions that he introduced in high energy physics would be represented as elements of Pi3S3 homotopy group, also represented by integers. In high energy physics, these integers would actually correspond to subatomic particles with different baryon numbers, right? So these different baryon numbers that you can see here would correspond to the different topological distinct ways of wrapping S3 sphere or field configuration on S3 sphere on that of another S3 sphere, right? So Pi3S3. And so what's interesting is that the model was introduced quite long ago, in the 60s, and much later Ed Wheaton was able to demonstrate that in a certain color limit of quantum chromodynamics, the quantum chromodynamics actually is consistent with Square model, or Square model is a certain limit of quantum chromodynamics. And so recently there is still a lot of interest in this type of model, in particular in order to describe subatomic nuclei with high baryon numbers. You can see, for example, different versions or varieties of that model even being discussed very recently. But what I will discuss with you today are slightly different types of topological solitons that would correspond to these elements in here in this table. So Pi2S2 topological solitons, which will be baby skyrmions, or skyrmions topologically similar to those studied in solid state non-centrosymmetric magnets, and also Pi3S2 topological solitons that we will also call Hopfians. But in addition, I will very briefly mention several other types of solitons as well. And so the system we'll discuss in which we'll realize this solitonic structure are ferromagnetic liquid crystals. So in here, we dope conventional thermotropic liquid crystal with ferromagnetic nanoplatelets, which are magnetically monodomain, and under certain preparation conditions, which I will not discuss in too many details due to time constraints, one can achieve the ferromagnetic ordering of these platelets when the single magnetically monodomain platelets will all order in the same direction with magnetization, with magnetic moments parallel to director, far-field director liquid crystal, and they will define the magnetization field, which in the ground state typically would be uniform. And so it's very interesting that for these soft magnets, we have a lot of very similar observations to those we know for solid-state magnetic systems. So, for example, you can have magnetic hysteresis loops like the one you can see in here. And now you could ask, why is it that in a system like this, we would have these types of localized solitonic field configurations that would be different topologically from this kind of uniform background, right, state, and why would they have a reason to exist, right? This is actually a very important question to ask, because there is a so-called Derek theorem that would tell us that it should not exist for energetic reasons when you have a harmonic type of potential, right? Or in when in the linear theory, when your force is linear. And so in high energy physics, Scherm was the one who proposed to overcome these constraints of Derek theorem by simply adding high order nonlinear terms, and then these solitonic structures, topological non-trivial structures, would emerge as solutions of differential equations that minimize some form of energy potential. And those would be, this is how you would get these different baryon numbers, right? Then corresponding to some energy minima, right, for these solitonic field configurations. Now, when we have liquid crystals or solid state ferromagnets, we can have also other reasons, other origins of non-harmonic free energy, or the Hamiltonian. So, for example, in the case when we have solid-state ferromagnets, in the simplest form, we can describe the Hamiltonian by the expression that you can see in here, where we have the exchange energy term, and then another chiral term, right, that makes this system nonlinear, and in some way it plays a similar role to how the high order nonlinear terms in nonlinear sigma model in high energy physics overcome the constraints of the Derek theorem, right? And so, so for solid state ferromagnets, we just have exchange energy term and Zoloshinsky-Moria term, the chiral term in here. When we have liquid crystal ferromagnets, and then here again we can add chiral additives and have a chiral term as well that will make the system preferring to form twisted field configurations in a limit when all of these Frank elastic constants made to be equal to each other, so in so-called one constant approximation, this expression can be reduced to the expression that we have in here under this one constant approximation, and with the relation between the two different types of constants we have in these two expressions, right? What this means is essentially that in one constant approximation we can map the problems we have in liquid crystals and magnets to each other, right? And so because the Hamiltonians are similar in both cases. And so now let's take a look at the different solitonic structures that we can have. So the simplest structure that we can have in higher dimensions beyond 1D would be these baby Schermions, right? So in here, in one type of structure, we have pi twist from center to periphery in all radial directions, and as you would map this field configuration from R2 or two-dimensional plane to S2, right, you will see you cover this entire sphere once, and so this defines a Schermion number, right, because mapping from R2 in here is equivalent to mapping from S2 to S2, so it's pi to S2 equal Z, and in this case equal 1. Now, in order to visualize another type of solitons that we'll discuss, the Hopf solitons, we need to recall the concept of preimage. So this is a region in three-dimensional space within which the spins of magnetization all point in the very same direction. And so here, with the help of this green isosurface, I visualize such region within which all the spins of soliton. We need to have these pre-images to have spatial form of closed loops, and these closed loops have to be linked with each other precisely the same number of time for all pre-images of all points on the S2 order parameter space, right? And so then the linking number is the topological invariant, so geometric interpretation of topological invariant. On top of it, this structure will have to be localized in all three spatial dimensions and confined in a uniform background without any singularities. So that's kind of a little bit hard to imagine how precisely this would happen, but we can realize such structures both in experiments and in numerical modeling, and I'll start from describing how we obtain them in numerical modeling. So in this case, we minimize the free energy in this form that I already discussed briefly on a three-dimensional large 3D grid, and then with the help of finite difference numerical approach, we also define the uniform far-field background, we can observe then these spatially localized three-dimensional structures, and here I depict one of them with the help of free energy isosurfaces. As you can see, within this localized structure, within most of the volume, we have relatively low free energy density, but there are regions of a little bit higher cost of free energy density as well. We can also, for the very same structure, visualize the isosurfaces of the so-called handedness parameter, which tells us both about both the direction and the rate of twist of demagnetization within this liquid crystal ferromagnet. So what we note is that when this structure is embedded in a uniform far-field background, within a large volume of the structure, we have the magnetization twisting in the very same direction as the chirality of the system would dictate, and this the rate of twisting is also very consistent with what you would expect for a chiral liquid crystal ferromagnet of a certain equilibrium pitch. But there are also regions in here at the top and bottom where handedness is of opposite type, and so the reason for presence of this small opposite handedness regions is that in order to embed the large volume of proper handedness of twist, we need to have these kind of sacrificial regions of opposite handedness in a certain location, and this is some form of a compromise that allows to relieve the system's frustration and embed this kind of twisted localized structure within a large volume of the solitonic configuration, but in expanse of presence of small regions of opposite twist.
Could I ask, what were the boundary conditions?
So in here it's a uniform far-field.
Okay.
So you need to embed in that uniform far-field.
Don't you need to add something like an isotropy or field in order to stabilize this fermion?
So in the solid-state magnetic systems, this is exactly the case. So the fermions would be in the bulk materials would be stable only in certain range of applied magnetic fields, right? In here, this doesn't have to be the case, because you can have effectively similar role played by boundary conditions, right? So when you essentially
I see. Okay.
these boundary conditions tend to unwind of solitons. So later we'll discuss two-dimensional counterparts of these, and in there, this will be a little bit kind of more important to emphasize as well. All right, so let's take a look at what these structures look like. So if I now look in the plane of such localized structure that's orthogonal to far-field magnetization, I will notice that the spins twist by 2 pi in all radial directions, and so the structure is continuous. But then in the plane which is orthogonal to this one and parallel to the far-field magnetization, I see that the structure is perfectly continuous. The spins are not forming any singularities anywhere, right? And you also have a lot of twisting along the far-field magnetization, right? So within most of the volume, as I already mentioned before, the twisting handedness matches that of the chiral liquid crystal ferromagnet in which we observe it. As I would now look at pre-images corresponding to regions within this three-dimensional volume where the magnetization points in that direction corresponding to points on S2, we see that these regions have closed loop-like shapes. And then for every pair of pre-images, we see that we have linking of these pre-images, and the linking number is always the same. So we can take a closer look at what happens here. So if we go smoothly from the south pole of the S2 sphere, we see that as the polar angle increases, for every constant polar angle, we have the pre-images tiling into tori, and then the largest torus that we will get will correspond to the north pole of the S2 sphere that will separate this three-dimensional localized region of the soliton from the uniform far-field background within which this solitonic structure is embedded. What's important is that for every pair of all of these pre-images, we'll have always the same linking number. So in this case, it will be 1. And so again, yet another look at what happens here. So for the south pole, we just have a single closed loop pre-image. As we change the polar angle, we get bigger and bigger tori that are formed by nested pre-images that all have shapes of closed loops, until we get to the north pole, right, that in its interior has all of these pre-images of all the points on S2, but in the exterior of it is a uniform far-field background, right, corresponding to what I defined by boundary conditions in my sample. And so, so the question is, this is in numerics. Numerics was actually inspired by experiments, but how do we sort of assure that we have the same stuff in experiments and in numerical modeling? So in here we took these field configurations that I was showing you earlier and computer simulated nonlinear optical polarizing images that would be obtained for different polarizations of femtosecond excitation light. And so these 3 images in here correspond to the plane that's orthogonal to the far-field background. And for excitation light with linear polarizations, marked in here, or circular polarization. And then those 3 simulated images would be corresponding to vertical cross-section that I was also showing, but also for different linear and circular polarizations. And so then in experiments, we can obtain the counterparts of these images. And so you can see a very good agreement between the simulated and experimental structures. Moreover, we can also compare not just cross-sectional images in three-dimensional space, but also the pre-images that we can reconstruct on the basis of analyzing these types of experimental and simulated images, right? So in here, you can see that the pre-image on the equator of S2 sphere, have the topologies of closed loops, and they also have peculiar geometric shapes, right? And you can see that in experiments and in computer simulations, they very closely agree with each other.
So what's the material that was used in the experiment?
It's a very common material, pentyl cyanobiphenyl, doped with chiral additive, CB15, and you add barium hexaferrite nanoplatelets.
Okay, and it just forms these skirmions all over the place.
Well, yeah, so you form that material, you add chiral additive,
Yeah.
then you have boundary conditions, and as you quench from isotropic phase, you have those conditions.
Okay.
Well, you have to set the boundary condition, no?
Yeah, well, that's a very common thing.
Yeah.
You need uniform background for those things.
In the numerics, you use the one elastic constant approximation.
No. So
Is the true elastic or the 5C?
all elastic constants of ICB. But then important thing that we checked additionally was whether these type of structures can be also stable under one constant approximation, and they can be stabilized in somewhat different conditions. Additionally, I should say that we also had Israel letters back in the end of 2018, where we, in numerical modeling, realized such structures in solid-state magnetic systems like MNSI and iron germanium. So, in a sense, they should be present in many different condensed matter systems. Here, we already see them in experiments and in modeling. In there, they still need to be discovered in experiments, but they should exist in undeveloped defined conditions.
How is it dependent on the system size?
Yeah, pitch of liquid crystal can be tunable, so you can have different dimensions. In magnetic systems, again, there is analog of pitch, that also can be tunable from sub 10 nanometers to 100 nanometers, and liquid crystals from 100 nanometers to hundreds of micrometers. So it depends on which system you are doing it.
But my question was something different. Do you need confinement to make these things stable? I mean, if you make the box bigger and bigger,
Yeah,
where
so
will they
it
go?
depends on which ones. There are different types, and I'll show a zoo of those guys.
Oh, I
But there are some that you don't need. There are some that you can do only in 2D. There are some that you can do in 3D, and so I'll show some 3D crystals as well.
So what's the relation between your elastic constants?
Um,
Are they of the same order, or one is bigger than
Yeah,
the
yeah, these are all of the same. Like real parameters for 5CB, independently measured, taken from experiments. That's why agreement is good, because you're not making too many approximations. All right, so now importantly, we can have many other types of solitons, and so I'm showing only very briefly here the soliton with opposite sign, elementary soliton, -1, so linking number would be -1. And then here, soliton with Q equal 2, so in this case, the pre-images would be linked 2 times, right? Because geometric interpretation of that topological invariant is the linking number, right? And so in here you can see when we have 2 pre-images, they would be always linked with each other 2 times, right? The linking number is 2. And so now, as we realize different types of topological solitons in these liquid crystal ferromagnets, and you apply external fields, either parallel or anti-parallel to the far field background, magnetization, right? then they shrink or expand as you would expect because in one case, so in here we have a linear coupling, right, between the magnetization and external magnetic field, B field. And so because of that, you either promote uniform background, lower energy, or vice versa, that region with somehow distorted field configuration, would expand depending on whether you apply field in parallel or anti-parallel fashion. And now under other conditions, we can also have these structures assembling into two-dimensional crystals, as you can see in here, so hexagonal lattices. And again, for the entire lattice, as we apply field in one direction, they shrink, in the other direction, they expand. And almost you get a feeling that they merge with each other, but still you can identify these topological non-trivial field configurations because in many ways they are knotted field lines, right, that you cannot destroy unless you destroy order or induce some singular defects within this volume, right? They are different from the uniform far-field background. What I showed were only very simple ones, simple topological solitons that we realized. So you could represent them simply as a hop link, right, of two pre-images. But the tables that you can see in here show the types of solitons that we also realized in both experiments and in computer simulation. So they are much more complex. And so, those different visualizations, they have either simplified linking diagrams of of two pre-images, right? So like, as you can see them depicted in here. And also we can have them in liquid crystals and in liquid crystal ferromagnets. So of course, in these two cases, the order parameter space is S2 or S2Z2. And these are the graph representations where the closed loop pre-images are simply shown as the filled circles, and then they can be linked with each other or not, depending on what type of solitonic structure we have. So the reason we have such a large variety is that, as I already discussed before, we have many integers, right, that describe the different elements, topologically distinct elements of this third homotopy group, pi3s2. So it's entire zoo where, as we already discussed, the geometric interpretation of the topological Hopf index invariant is the linking number, right? So when we have a Hopf link, then the linking number is 1. When we have Solomon link or other realizations of it with two times linked pre-images, we have Hopf index equal to 2. So the question is, as you could see in this case, right, we have the order parameter space being the S2 sphere, and the space from which you are mapping is already S3 sphere, right? Because R3 three-dimensional space, as we discussed earlier, for uniform far-field background, this can be fully represented on S3 sphere. But could we perhaps also have some other types of solitons that would get us a little bit closer to these Skyrm solitons pi3s3? And so that's indeed possible, because we can also have liquid crystal chiral ferromagnets that lack uniaxial symmetry, where the magnetic nanoplatelets under some surface anchoring conditions on the particle surfaces tend to align in an orientation tilted with normal to the platelet surface, tilted with respect to the far-field liquid crystal director. And then the magnetization becomes tilted with respect to far-field liquid crystal director. And so in these types of structures, we can realize solitonic field configurations in a triad of vector fields. So in all three vector fields, you have smooth configuration being also considered. So Pi3S, 3Z2, in particular by Shankar. So they are sometimes also called Shankar skyrmions or Shankar solitons. And so here I'm just showing you how these field configurations look like when we separately visualize within such a structure the three different fields that I was showing to you. And so what's interesting is that these solitonic structures oftentimes exhibit particle-like behavior, which is very much dependent on material properties, confinement, and applied external fields. So in here, for example, you see two such solitons interacting with each other, and in this particular case, the interaction is attractive. We can see that under some conditions we can have peri-interaction potential on the order of 1000 K-Boltzmann T, and these particle-like solitons can be localized in all three spatial dimensions. So you can see from this video that the particles are attracted to each other while moving in both lateral and axial directions, and then self-assemble it into some structure, right? And so as you have many of them, they can self-assemble into crystallites of different types. And so again, and here's because of presence of these attractive interactions. As you then change applied external field just by 1 volt or so, you can see that we have very strong deformations of the lattice, very significant electrostriction. Moreover, we can also observe that the symmetries of organization of these shape and isometric solitonic structures can be changing, for example, from unidirectional alignment, as in this case, to the one where we have some anticlinic tilting within the different layers of such a self-assembled lattice. In numerical modeling, we can see that not only under some conditions the individual solitons can have energy, so when we apply external field, can have energy lower than that of the background, but also the crystallites that we form can have, the three-dimensional crystals can have lower energy than the uniform background. And so you can see in here a demonstration that indeed we have self-assembly not only in lateral dimensions but also across the sample thickness when we pull with laser tweezers one crystallite beneath the other one. And so those are some other examples that we demonstrate using polarizing optical microscopy and bright field imaging, showing that the self-assembly is truly three-dimensional in nature, and we have these different types of electrostriction and reconfigurable assembly of such solitonic structures where we can have both open and closed lattice, crystal lattices, and under different conditions the interactions between such solitons can be very strong, with potentials on the order of thousands of K-Boltzmann T, or not so strong, only in the range of 10 K-Boltzmann T, and so on. So what we discussed here were three-dimensional topological solitons, but now we will go back to the lower dimensional analogs, right, which would be localized only in um, 2 dimensions, but will be effectively translationally invariant in the 3rd dimension, right? And so in this case, we have that pi twisting from center to periphery. So, right, so if you look in a 2-dimensional plane, this is the field configuration that we typically would have, but the interaction with confining surfaces can also morph this field configuration in some way, and so so that it wouldn't be perfectly translationally invariant under relatively strong surface boundary conditions, right? So in here you can see 2 extreme examples, right, of strong and weak and strong surface boundary conditions. And what they correspond to is shown in here numerically for us, right? So again, this is a top view of such skyrmionic structure that has field configuration that fully covers as to sphere. But then as we look at the side view, when the anchoring is weak, we just have this structure translationally invariant across the entire sample thickness, and it's 2-dimensional in nature. However, if the anchoring is strong, then we can have the point defects of the same class of homotopy group as the skyrmions, pi2s2, right, capping this skyrmionic tube close to the 2 confining surfaces. And so here you can see those under the experiment. So in intermediate cases, these defects can be localized not in bulk but at surfaces, and they can become virtual when you have the weak surface anchoring boundary conditions. And so now, so this is one such solitonic structure, but the question that one could ask is, could we have a higher degree 2-dimensional skyrmions, right? Because as I was telling earlier, for such 2-dimensional structure, the skyrmion number is 1 because as we map from R2 or corresponding to S2 to the order parameter space S2, we cover the sphere exactly once. And so how about the skyrmions with larger topological degrees, so skyrmion numbers? And so, that of course could be inspired by the fact that in nuclear and high energy physics you have all of these different higher degree skyrmion structures that correspond to the subatomic particles with different variant numbers. So one could simply think about extending the twisting of the magnetization or director field as you go from center to periphery, right? So for elementary skyrmion, we just twisted by 2 pi. And so you could think about, well, why not twist in pi more, right, in all radial directions? And perhaps then we'll cover the order parameter space as to sphere one more time. But that's not the case. Actually, in this case, you are getting the skyrmion number equal to 0, and the structure becomes equivalent to the uniform far-field background. And the reason is that as you are wrapping this as to sphere, then as you twist pi again, you are unwrapping it. And in the end, you have nothing. And so this type of structure is called skyrmionium. In fact, if you twist an integer number of times, then you could have also another structure that in magnetic systems people called target skyrmions, right? When you can have some integer number of twists of magnetization or director from center to periphery. And however, as I already mentioned, in all of these cases, from the standpoint of view of topology, you're not getting anything new because you always have either 0 or -1 or +1 depending on convention how you define the Skyrmion number, right? But these structures are topologically unstable because there is a pathway with which it is topologically equivalent. As you are changing the number of twists, as in this movie, your Skyrmion number is changing between integer elementary 1 and 0 and elementary 1. Right? So with this, we cannot then get this variety of topological degrees that we also have in high energy physics, right? And so the question is, how could one possibly do something like this? So recently, in collaboration with the research group of Mark Dennis at University of Birmingham, which is the site where Skyrm was proposing the original, Skyrm solitons, we came up with the concept of Skyrmion bags, where essentially what you do is you take a Skyrmion, open it up, and create anti-Skyrmions within it. And so then that outer Skyrmion becomes what we call Skyrmion bag. So in here you can see the demonstration of such Skyrmions in computer simulations and also their realization in experiments. And indeed, as you would be mapping such field configurations to the order parameter space as to sphere, you would cover it different integer number of times, right? So, for example, this is corresponding to the Skyrmion bag in here. So with this approach, one can get any integer as topological degree for such two-dimensional Skyrmionic structures. But the question is also whether it would be possible to obtain such configurations with higher degrees through the interactions between elementary Skyrmions. Because this is exactly what happens in high energy physics, right? And so to discuss this, during the next portion of my presentation, I'll show you how we obtain different clusters of Skyrmions as they interact in and out of equilibrium under different conditions of applied external field. So in here we have the elementary Skyrmion, and then we apply an external field perpendicular to the screen, right? So along the far field background, and the material in this case has a negative dielectric anisotropy, and so the structure that was axially symmetric originally will have to morph because as you apply external field, you're tilting the background field around the liquid crystal Skyrmion. And so in here you can see such a structure as it morphed at applied field of about 3.1 volt, and it's represented with the colors corresponding to the different points on S2 sphere. So what's important to note is that as this structure morphed, the Skyrmion number did not change, right? So topology, the field configuration is topologically protected, and as you would map this field configuration to the S2 sphere, you would again get unity in this case. Now, if you, however, apply field and turn it off, something even more interesting happens, right? So here we have both experiments and computer simulations, where in the modeling we have only rotational dynamics taken into account. So we only have rotational viscosity and the corresponding torque. What we do in experiments, we take a video as we apply voltage and turn it off. So this would be such a electric signal with high carrier frequency, and then we modulate it with a certain period. And so what we see in experiments is that as we turn the voltage on and off, the skyrmion shifts in the two opposite directions as we turn it on and off. But this shifting is asymmetric, and so when we turn it on and off many times, the skyrmion simply walks in a certain direction. And the same can be seen also in computer simulation. So as director structure is evolving toward equilibrium, and we turn the voltage on and off, we can see that that evolution results also in asymmetric shifting, as you can see in here. Very similar to that we know also in experiments. And so eventually this results in the asymmetric skyrmion that we obtained by applying external field, simply moving in different directions. And so again, in both computer simulations and experiments, we can look at the details of evolution of the field configurations, and we can understand where it comes from. So the response of liquid crystal is highly asymmetric to applying field on and turning it off, and it's non-reciprocal. So because of that, the localized field configuration shifts in a certain direction determined by the symmetry of the director structure. And also I should note that the reason for this asymmetry in response and evolution of director field is that as we apply voltage on, we have electric torque, elastic torque present, and also viscous torque due to rotational viscosity competing with them. But when we turn voltage off, in this case, only elastic and viscous torque are present. Very similar to the case of liquid crystal displays, where the turn on and off times are typically different for this very same reason. But because here we have two-dimensional spatially localized structure, as we apply voltage on and turn it off, it evolves in a symmetric way that results in a translation of such a structure. So when we have multiple skyrmions, they start interacting with each other, and those are interactions largely mediated by liquid crystal elasticity, but out of equilibrium, because the voltage is never constant, they never reach equilibrium field configuration, and during this modulation of applied electric field, they at some moments want to attract each other, at another moment they want to repel each other, and so in the end this results in a very rich behavior of such out equilibrium system. So one thing that you note, probably looking at these meandering chains of skyrmions, is that under some conditions they tend to assemble into chains, and the reason is because the structures become dipolar in nature, and as we would expand the field configuration at distances large from such localized structure, we would see that the leading order multiples would be dipoles, and the interactions are effectively dipolar between them, but they are much more complex than what you could describe with simply dipoles interacting with each other, because as you're modulating applied electric field, you're tilting the dipoles to be more in plane of the sample or sticking perpendicular to the sample, depending on instantaneous voltage, And so it's like oscillating the dipoles with periodically modulated amplitude as they interact with each other. So now we can see what happens if we go from several of them or hundreds of them to thousands and millions in a large sample like the one in here. We can see that the ordering of such dipolar-like skyrmions, we will see that with time, the skyrmions establish polar order parameter, right, which we characterize as Q defined in here. So all these vectors that connect the south and north pole pre-images start pointing in the same direction, and also the velocity order parameter, so they all start moving in the same direction within several seconds. Also, within such large schools of skyrmions, we see quite large number density fluctuations. So within a certain area, like for example the one in here, but perhaps larger, we would see different numbers of skyrmions passing through it within given amount of time. So how can we understand this rich behavior of skyrmion structures under auto-equilibrium conditions? So first of all, the individual skyrmions interact with each other repulsively at no applied field, right? And so you can think about them as dipoles which are perpendicular to the two-dimensional plane in which they are confined and they are repelling each other. However, as you apply external field, you are progressively tilting these dipoles to be more and more in plane, and then they start interacting attractively when they are one behind each other, and when side by side they repel each other, right? So this is given the origin to the skyrmion chains that we discussed before. But even richer behavior is established when we go from a few skyrmions. So these all data of interaction pair potential have been established for just two moving skyrmions. However, if we have many of them, we can see that they develop certain type of cohesion within the large schools of skyrmions, which is manifested in here by the deep and many-body interaction potential. And so in numerical modeling, which we can do only for a small number of such skyrmionic structures, as we evolve director field configuration, we can also see different types of clustering, so either linear chains or this kind of more isotropic clusters. And so you can see here computer simulated and experimental images agree with each other quite well as under these conditions as particles move. And so let's now see the different types of collective motions that we can see locally within this very large schools of skyrmions as they move. So under small number densities of skyrmionic particles, we can see that they move more or less as individuals within the bigger schools, and within different areas we can do statistical analysis of root mean square versus mean, and so in this case we can see evidence for giant number fluctuations where alpha in this log-log plot is larger than 0.5, which would correspond to particles under equilibrium conditions, for example, undergoing Brownian motion. On the other hand, as we change voltage and also the density of skyrmions, we can see that they start clustering, and those clusters can be either relatively isotropic or more chain-like. And under these conditions, again, we see evidence for giant number fluctuations with slightly different values of alpha. We can systematically characterize the different types of active and passive equilibrium behavior of such solitonic field configurations under the packing fractions that we have. When voltages are relatively small, the skyrmions tend to repel from each other, and so under high densities they will start to crystallize, but otherwise at small densities you see more gas-like behavior. Now, as we go to larger voltages, as you recall, they become asymmetric, right? And so in the case if we have high frequencies, high enough so that the liquid crystal director does not have time to follow, right? It simply responds to average applied electric field. Then we have different types of static structures, either these isotropic clusters or much more anisotropic linear chains at the intermediate applied voltages. And we can understand them very well by, this very toy representation of the pre-image dipoles that are tilted in different way with respect to the confining two-dimensional plane. So in the case when they are in the plane, they form linear chains, as you would expect in analogy with electrostatics. However, in the intermediate range of frequencies of modulation, which are comparable to the response or periods of modulation comparable to the response time of liquid crystal, the director field is always out of equilibrium. And so in this case, we see these dynamic states that correspond to out of equilibrium collective behavior. In yet lower frequencies, the skyrmions become unstable because of different types of hydrodynamic instabilities that form. You could ask what happens if you have even larger number densities of such skyrmionic structures. So you can see that they still exhibit all kinds of very rich collective motions, and you can characterize the crystallites and defects, the different grain boundary defects in between them, so represented in here on the basis of coding different skyrmions with different numbers of neighbors, and so you have all kinds of 5, 7 defects around the location of the boundaries. And so when we see such moving structures of skyrmions on large scale, it's very interesting to look at the long-range organization of such skyrmionic structures, which we can characterize by the hexatic order parameter, so defined in this form. And so what's interesting is that when the skyrmions here don't move, they're just created initially with this very large number density, then the hexatic order parameter is 0, which means that the different crystalloids separated by grand boundaries are uncorrelated in their orientations with each other. However, when the motion is established, then we see that this hexatic order parameter becomes relatively large, and so we essentially have the orientational hexatic ordering induced by the collective motion of skyrmions in this case. Well, so this brings me to the conclusions. I realize I run over time a little bit. Maybe we should have started 15 minutes before 5 or 4. But anyway, I hope I showed you that the skyrmionic and Hopfian structures in liquid crystals exhibit particle-like behavior, and they can be a good test bed for the studies of topological and non-trivial solitonic field configurations in condensed matter and beyond. They indeed reach and collective dynamics, which can mimic behavior in many ways of other types of particles we often work with, including colloids, atoms, and active particles as well. Thank you for your attention.
A question. I was wondering if you change the liquid crystal and choose one with negative diamagnetic anisotropy, do you expect differences? Because these little bits are magnetic to start with, and the 5Cb, the diamagnetic anisotropy is positive. But if you have a saturated liquid crystal, is that a lie?
Yeah, so the response there is to very big magnetic fields of the order of several Gauss or even 1 Gauss, and the which diamagnetic response of 5Cb Gauss. Yeah, it's like the response of even Earth's field has effect. So it's extremely strong response, unlike the diamagnetic liquid crystal response, which requires typically a kilogauss, right?
So what's the Curie temperature of the? It's very high, I guess.
Well, so you will, as you heat, you will go to isotropic phase of liquid crystal.
Yeah, but the Curie
But
temperature of the
platelets-
magnetic is way out, right?
Yeah, much higher. For barium hexaferrite would
So
be.
you do not have a way, if you add much lower Curie temperature, you could sort of melt the magnetic by keeping the.
Before, right? Maybe one could find materials that would allow to do it, but not resistant.
No.
So it was very interesting talk, by the way. I was interested in the simulation you did on the box with constant magnetization or constant magnetization around the boundary, and you got this inhomogeneous solution. Now, if you decrease the size of the box, keep it the same shape, but decrease the size, do you still get the solution, or is there a size effect?
So, in the one that I was showing you, what matters is how far the top and bottom surfaces are apart. On the side faces, we actually have periodic boundary conditions.
Okay.
So and that doesn't matter too much.
Okay.
But for you to unwind liquid crystal, not to form some helicoidal structure, you want to keep the two top and bottom surfaces about equilibrium pitch apart from each other.
Okay.
If it's much larger, some other structures will form.
So there is a
this
size
is just
Yeah.
in this case there is, right?
Yeah.
But then there are other ones where I was showing you three-dimensional crystals. In there is no such size effect. So under some applied external field, and this relates to your question as well, you don't need the boundary effect, but that requires applied external field.
I have a really stupid question. How do you control the number of skyrmions? How do you go from the dilute to the dense regime?
I have students with magic hands.
So you just do it.
Yeah, so there are
This is
different
not like
ways.
there is
Yeah.
particle conservation, so illuminate.
There
How
are
do you
many
do it?
different ways of creating them. One is with laser tweezers. You can
Oh,
treat one
you
by one.
defect with lasers. Yes, I know you're
But
always
there are,
playing tricks
but
with
there are
lasers.
also
and liquid
but
crystals.
there are also ways of
It's
mass
actually
producing
creating the
them.
defects by lasers.
No, you can, yeah, and so this is a way to do it one by one, if you
Or
want
you do
to.
an optical lens. But I mean,
But if
they
you
will
do,
just not
yeah.
come out. I mean, you
But
wouldn't
if you
form
quench
defects.
from isotropic, you just have it for free.
Oh, because
because
you
they-
quench.
Yeah, because they are
Then
lower
how do you
energy
you
than.
control the density just by the quench rate or the some
Yeah.
And you form those lattices?
Mhm.
Wonderful. Then there is a second question, which is more to do with the very last part, which, if I recall some of the talks on active matter and so on, what you seem to have here is a much, much larger velocity, average velocity than I see in a system. And your experimental system determines the average velocity of the flop. I don't know what you want to call it.
I mean, those are not so large. They're on the order of micrometer per second.
They just
So,
look
you
large
know,
to
the
me.
fish and cows are certainly faster.
But it must depend on the intensity of the field, I mean, or what.
Mhm.
What is the control parameter for that average
Well, so
drift velocity?
yeah, I mean, we can control this amplitude of field with modulation frequency, but in our case, it's not super fast
Okay,
because.
just looked, it was then just an impression,
Mhm.
larger than. And the final question, I mean, your pictures, last pictures, reminded me very much of the dipolar granular systems. And this is what you have effectively. Some dipoles, you put an electric field, and I mean, there are some papers on dipolar,
Or just magnetic particles.
or
It's-
just
yeah,
magnetic particles.
yeah.
So how do your, I know to get there you have a very different process, and then by miracle these things simplify, and the collective effects do look like magnetic or dipole is just vibrated or
Mhm.
with an electric field or whatever.
Right. I mean, even not just magnetic, more general dipoles, right? Because, like, you know, you can have magnetic chains, right? But you could have also liquid crystal colloidal chains, right? Where
Sure,
you
sure,
have
no.
those dipoles. And
To rephrase the question, I mean, do you actually end up with something which is effectively like a simpler, or at least a system that has been studied in different colloidal or even magnetic particles?
Well, and so you see what is interesting, I think, to me very much is that you can have equilibrium states, right? Let me get to this diagram, right? Under these equilibrium conditions, they self-assemble it, right? When you oscillate field very fast and director cannot follow, right? They self-assemble it and they are there, they are static structures, you know, and you can explain every single detail why this cluster formed with that one, how they tilted, you know, very simple. Now, if you oscillate them and they start moving and they exhibit these collective motions, I think there it's much more complex because, you know, these motions develop spontaneously. They initially move in all different directions, and all of a sudden they synchronize, very much like in active matter, right? But energy in here is supplied to the entire sample, right?
But it's a field which does not couple with motion. The field is like
It's not
vibrating
coupled,
granular.
yeah. So the field is perpendicular to motion's
Right,
directions.
right. So
And
it's,
the
so people
conversion of
argue that
energy
that
is
would be like feeding or getting particle by particle.
right. So it's on individual basis,
Yeah,
right? That you
individual
convert the energy, but they figure out how to move collectively and.
Very nice, yeah.
yeah.
In liquids, you have vortices, the chains for vortices, and which can unlock. But here, maybe not because of the asymmetry caused by the same process.
I mean, you know, I was showing you much kind of less directional motion, right? And some, yeah, like here. And you know, I just don't have time to show all movies, but you know, there are all kinds of vortices,
Okay,
you know,
right.
they can move and all kinds of crazy fashions. Yeah.
Because you could have then a kind of Custer-Stowles transition with the unlocking of the vortices. Which would
But typically, if you try to drive the magnetic skyrmion with the field, it's not going to go straight. It will kind of go to the boundary because it has this type of motion because of the Tilly equations.
Yeah.
So in here, it seems that you just drive it straight, yes.
Well, not really. The field is actually this way, you
Yeah.
see.
Uh-huh.
And so these all directions are chosen spontaneously. And when you have few of them, not so many, they don't figure out how to move together, right?
No, but I mean,
But when you have some higher density, then they start moving together, they still oscillate in this way.
no, I'm talking about single one. So you were showing this.
In single
movements,
one
but
also
single one moves.
moves like this,
Ah, I see.
but
Okay.
but you oscillate field that way,
Okay.
right? And so it's kind of direction of motion is chosen by that particle itself on the basis of some spontaneous symmetry breaking, because the tilting of the field could be this way or that way or this way, right? And then it happens somehow, and then that determines how this motion evolves.
Okay.
But you know, I'm very familiar with magnetic systems, right, and racetrack memories. That's one of the problems that you know, they could go to the side,
Yeah, yeah.
right? Yeah. So.
I mean, they typically try to drive it now with the currents, but
Mhm.
with the currents they can control it.
Right. Yeah.
I would also like one question, if I may. No, so you showed this richness of the fermions, of the solitonic structures, right?
Mm-hmm.
But can you really design one? Say, I want that one.
Yeah, well, that was part of my question.
So
And then can you distinguish them when they move like
no,
that?
I mean, is it really
Yeah.
that you? I mean, one line is, of course, I understand it's quench line, right? You can do it optically, right? And I guess with optics, can you really favor, right, which one you get? Or I mean, how can you say I want that one?
Yeah. You know, so first of all, there are different ones: pi 2s2 or pi
Yeah.
3s2.
What is it? Second?
You know, I think it depends a little bit.
Yes. Okay.
So you see in here, all of these have been generated with lasers. You take one skyrmion, you open it, you generate one inside, and so on. So this is live printing, right? And this is stabilizing them, because you could see that when you know, do this kind of skyrmionium, it's unstable, but those are, because they're topologically protected, they're distinct from each other. Now, but you know, what I sort of forgot to emphasize is that when you have this type of clusters, right, the skyrmion numbers add, you know, so effectively you have like and high energy, they are forming higher degree through interactions, right, not through placing one inside of the other. So you see here, they can spontaneously assemble into effectively analog of high barrier number particle, right? Or you could generate them one inside each other with certain geometry, you know, and so you could choose which of those you like, and each of them can be realized. But then when it comes to sort of this,
This one, for example.
Yeah, those pictures.
This is like advanced, right?
No.
yeah, so no, I mean, I just want this.
Something like this, yeah.
Yeah, this was all spontaneous. So you quench from the isotropic phase, and all of these are local minimum of free energy, or global in some cases, right? And then you get one of those, and then you can start it. There are certain, you know, ways of defining. Again, you see those look a little bit different, right? Typically, the higher degree, the bigger they are also. You don't have to melt entire sample. You can melt liquid crystal locally, and then one of those structures will appear.
I think we stop now. Yeah, thank you.
So is it,